You're walking the track, and the moment you step onto the bridge, you know the rules just changed. A geometry fault on plain line, you can tamp it, but on a bridge, it's just not that simple. The ballast might be shallow, that limits the tamping options. The sleepers can be tight to the structure, so slewing, again, not possible. And the track might be directly fixed to the bridge structure, so it's just not that easy. And the thing about bridges, the problems aren't random. They follow the bridge design type, from arches to steelwork to timber. Each one brings different risks in a different way. Know the bridge, and you know what's coming. Track typically sits on ballast. Its position can be managed by tamping, lifting, and slewing. Because of this flexibility, it's considered to be floating. Bridges are different. They have a fixed position, height, and structural form. You can't shift them sideways, raise them easily, or adjust their support conditions. Once built, their location and design can't be adjusted like the rest of the track. Just think of the work needed to demolish and move a bridge. It means you need to think differently when you approach them, because things start to get difficult. When floating track meets fixed structure, you get a conflict. Stiffness changes. Suddenly, a flexible foundation becomes rigid. Loads are transferred to the rails and fastenings, instead of being absorbed and spread through the ballast. Drainage is compromised. Reduced ballast depth and limited outlets for water can often mean trapped water, ballast fouling, and ultimately wet spots. Sleeper end clearance becomes minimal. The structure might provide some lateral resistance, but prevents slewing and makes sleeper changing very difficult. On plain line, you can remove and reinstate the ballast shoulder to gain access. That option doesn't exist, where instead of a ballast shoulder, you have the structure. In some cases, the sleepers or timbers are actually directly attached to the structure, removing any flexibility at all. Geometry faults behave differently. Poor initial design can become locked in due to the structure restricting realignment or vertical lift. Understand the bridge deck type lets you predict how, where, and why problems will appear. If you're finding this useful so far and want to build your confidence in track geometry and curve design, I have a free horizontal geometry email course that you'll love. It's designed for anyone looking to strengthen their understanding of the fundamentals, whether you're new to track or just want a proper refresher. The link's in the description and in the top right hand corner now. These are the hallmark of the UK railway network. Victorian built, over a century old and still performing. A peak of engineering from a time with far less mechanisation and none of our modern technology. They range from short spans over roads to long viaducts. Many of these have been carrying trains for over 150 years. The track often sits on fill above the arches, but that fill holds moisture. Over time, this causes degradation, which leads to drainage issues and uneven support for the track above. The parapet walls down the side often have to be held in place by steel tie bars. Modern trains generate lateral loads far beyond what the Victorians could ever have imagined. Combined with a track lift and increased ballast loading during renewal activities, this can add significant outward pressure. 9 Elms is a sobering example. A brick parapet collapsed onto the road below during engineering works. And it's not an isolated incident. In 2023, services between Newcastle and Mopeth were suspended at Plessey after the parapet wall movement was spotted during engineering works. No trains were derailed, but the incident forced emergency repairs and served as a stark reminder of what can happen when retaining structures begin to shift. So, the track problems. Long-term settlement, often caused by deterioration of the fill material or slow subsidence of the support structure itself. Poor drainage. The fill we spoke about traps water, which can lead to wet beds and the pumping of the track. There's limited amount of lift that can be applied, and the risk of overloading the structure is very real. Structural failure. These bridges deteriorate and fail. Bulging or cracking may be subtle, which makes them easy to miss during inspection and harder to manage over time. Typically spanning roads, rivers, or underpasses, these bridges use steel beams or plates with direct fix or ballasted track tops. Steel, it expands and contracts with temperature, and while this is well understood structurally, it can impact the track also. Network Rail and RSSB documents highlight that if expansion is not properly managed with the correct bearings or joints, it can transfer stress onto the rails and fastenings, leading to creep or distortion. Rail creep and geometry shift over metal decks has been observed in inspection records, particularly where expansion isn't being properly accommodated. You'll often find on these bridges a low ballast depth under sleepers due to the structured depth itself. Sleeper ends again hard up against the structure, making lateral adjustment very difficult. And then that deck movement can start to affect the geometry over time due to the thermal movement and the stiffness transitions. The key maintenance concerns is not just about the ballast, it's the steel itself. Corrosion, deformation and fatigue build up over time. Poorly maintained steel decks can deform, crack or lose integrity at the joints and connections, and in severe cases can lead to ballast dropping through and then loss of track support. Add to that rail creep due to thermal cycling, as well as tamping restrictions to avoid damaging the bridge deck below. More often seen on freight or low-speed lines, these cross timbers sit directly onto the bridge structure. There's no ballast between the sleepers and the bridge, so no wet beds, but also no vertical or horizontal flexibility without major works. The track geometry is held by the fastenings and the sleeper integrity. The problems that occur: timber decay over time, which reduces the strength and holding capacity. The need to use packing to maintain the track level, which can introduce uneven support, and it's not a long-term fix. The holding down bolts can work loose, breaking that link between the structure and the track, especially in those older or degraded timbers. With no ballast, it's all on the timber, screws and bolts alone, and this challenges it. You can't realign the track that easily. Renewal of cross-timber bridges often requires access from underneath, which can include scaffolding, working over water, or getting into confined spaces, all to loosen off those timbers. And then there's the screws. These can work loose, as they're taking a lot of force. So I've saved the best or worst for last. Longitudinal timber bridges. These decks use long timbers running under each rail. Typical sections might be 300mm by 250mm deep. The base plates are fixed directly on top. The support width is limited. Clearance between the edge of the base plate and the timber edge can be very minimal, meaning less strength and increased risk of the timber splitting. These bridge types have caused major failures. The barking derailment exposed exactly this risk. The surface looked fine, inside, rotten timber. The result was rapid geometry failure and derailment, leading to significant damage along the length of the track. So the things to remember about longitudinal timber bridges: hidden rot weakens the timber internally. You have to use long, high tensile screws to resist the dynamic loads, which tells you how much force is going through that system. Voiding at the ends, known as the flying ends, where the timber overhangs its supporting structure. This creates flex and lifting, especially at the run in and run out of the timber. These voids might only be visible when a train passes and are hard to detect during normal inspection, but they need to be treated. And when it comes to renewal, this is complex. You need hardwoods like Eiki or Greenheart. The work's got to be undertaken by experienced teams. The possession time planning is difficult due to those long installation times, and then timber availability and cost can also be a constraint. Also, let's not forget, sourcing tropical hardwoods does carry a big environmental impact, something to consider. Even if the bridge itself is sound, the interface with the surrounding track is where geometry issues can really start. You're going from floating formation to a fixed structure. This change causes voiding or top faults at the interface, sudden changes in settlement behaviour of the track, twist and other alignment faults. Transitions need designing. You might need approach slabs to spread the stiffness, GSLs or polymer treatments to create a gradual transition of stiffness between track and structure, controlled lifting regimes that don't overload the structure. These aren't just optional extras, they directly reduce fault reoccurrence. Failure to design the transition properly, and it will become a fault hotspot for years. So each bridge type brings its own risks and things to remember. Let's run them back. Brick arches. Check your drainage pathways. Where is the water getting away from the bridge? Monitor the structural movement and remember the tie bars that might be buried in the ballast or even deeper. Watch for long-term settlement trends and movement within the structure. Look out for cracks in the arch barrel or the parapet walls. Metal decks. Maintain the steel surfaces for corrosion and fatigue. Inspect the interfaces and the fastenings regularly. Respect the tamping limits and remember to be aware of expansion. Check bearing condition if they're present. Bearings allow the movement between the bridge and the substructure, and if these seize or degrade, the stresses are transferred onto that track above. Cross and longitudinal timber decks. Monitor the decay, both internally and externally. Maintain the holding down systems. These are the key links between those sleepers, bearers, and the structure below. Plan renewals well in advance. Renewing these assets is a time-consuming and specialist job that requires specific access, especially from below. A bridge isn't just a structure, it's a constraint and a maintenance challenge waiting to grow if you ignore it. Just a reminder, if you want to build up your knowledge of alignment, transitions, and curve design, the horizontal track geometry course is free to sign up for. You'll find the link in the description below, and if you want more of these breakdowns, tunnels, level crossings, and platforms, let me know in the comments.